So we put one over here, and then here, here, right. So the more hydrogen bonding we have is means there's a higher melting point, okay? Because it's more intermolecular forces to overcome compared to like a little bit of hydrogen bonding. Like for example, just have this one over here. So which one do you think is going to be harder to break? Would it be like this one or would it be this one? Obviously, it's going to be this one because there's more bonds that you need to break through, which means that it takes more energy in order to break the bonds, which means that it has a higher melting point and stuff. Okay? Because there's more energy for it to for it to break the heat of fusion, right? Now, how does this impact life on Earth, right? So, because there's a higher melting point, it allows Earth to sustain a normal temperature because Earth can now hold a lot of heat, right? So if Earth had like a lower melting point like this, then the heat of fusion would be broken down pretty easily, right? And then that means and then that would mean that like it wouldn't really stay icy for a long time. Like Earth would not be able to like stay ice. Like like Antarctica and stuff like that. It's Antarctica's only there because Earth has a higher melting point and stuff. For example, if we had like an ice cube over here versus like look, we have two ice cubes over here, right? This ice cube is put under like a fire, and this ice cube is just like normal. It's not put under anything, right? Um, Obviously this ice cube's gonna melt like way quicker than this one, right? Um, and that is because it has like a lower melting point, right? Um, yeah, or if we put like ice cubes with like salt. Salt actually lowers the melting point of like ice too. So this one's gonna have a lower melting point, which impacts the property of life on Earth because when this ice cube melts and like becomes like a lower like melting point, whatever, then it shows it can't really sustain heat for long, which is gonna make the Earth like heat up unnaturally long. Okay. That same thing goes for heat of fusion. Like the more hydrogen bonding you have, it affects the melting and boiling points, right? Now let's talk about heat of vaporization. Heat of vaporization. Excuse me for my bad handwriting. Okay. So if the hydrogen bonding was not there, then the water will boil quicker and get hotter. Now this kind of ties into melting point, right? And this also ties into boiling point as well. As we stated before, the more hydrogen bonding there is, more hyd bonding, it equals more intermolecular forces to overcome. Because the more bonding there is and more like intermolecular forces to overcome, the more energy it takes to overcome those bonds, which means there's going to be a higher melting point because you need a lot of energy to break through that melting point and stuff, right? So, if the hydrogen bonding was not there, then water would boil much quicker and it would get much hotter, and that's how hydrogen bonding impacts the property of heat of vaporization, right? Now, how does this impact life on Earth? We have Earth over here. How does this impact life on Earth? Now, we need hydrogen bonding, otherwise it's going to vaporize much quicker. Otherwise, the oceans are going to like vaporize much quicker, and oceans are going to evaporate, and we won't really have as much water on Earth, right? As we said before, if it doesn't take a lot of energy to overcome the boiling point, then that means everything is just going to boil like much quicker, right? And then things are going to evaporate. But because Earth has a much higher boiling point and everything, then the oceans are stable. It doesn't really evaporate as quickly, and we can easily go through like the cycle of life, and it's like the water cycle and stuff. Now, finally, we have specific heat capacity. How does this relate to hydrogen bonding, and what is its result of life on Earth? So, there is a higher specific heat capacity compared to other substances because of hydrogen bonding, right? As you might have known, the specific heat capacity for like I think it is metal or some kind of metal, right? Specific heat capacity for iron, I think, is 0.440 joules per grams of Celsius. That's for solid and stuff. But for ice, it is 2.03 joules per Celsius, right? Solid. That's for ice, right? And so because this has a higher specific heat capacity, it's because of hydrogen bonding. And the more hydrogen bonding there is, it's harder to overcome those intermolecular forces, which require more energy, right? So specific heat capacity is basically the amount of energy required to overcome, to raise the temperature of 1 gram of a substance by 1 degree Celsius, right? And the more energy we need, it's gonna lead to a higher specific heat capacity. Now, how does this result life on? How does this impact life on Earth? Right? Because ice has a higher specific heat capacity and so does water. It's able to sustain life because it could trap the heat from the sun and everything. The lower part of the ocean will not freeze because of the high specific heat capacity. So if you think about this, you think about the ocean, right? This part of the ocean, like the very top, it freezes over in the winter, right? But as you get lower and stuff, as you get lower down in the ocean, it stays normal because of a high specific heat capacity. Um, because it takes a lot of energy to overcome to like freeze every single part of the ocean, right? But if it had like a lower specific heat capacity, then during winter the entire ocean would freeze, not rather just like a specific part. Okay. Thank you guys so much for watching this video, and I hope the video really helped. And yeah, please get an A on your benchmark exam.